Hello and welcome back to SVSU's online tutoring. My name is Joel and today we will be looking at section 7.2, simplifying radical expressions, and the topic for this video will be simplifying radicals. So in the previous section we laid out a bunch of definitions and we even looked at a couple functions for evaluating radicals. But now we want to actually simplify those radicals into manageable parts or manageable numbers. So, for instance, if I had the square root of 12, how would I go about simplifying this? Well, what I want to do is that I want to take 12 and create a factor tree. So, what that means is taking 12 and figuring out what the factors are for it. So I have 6 and 2, right? And then 2 can't be broken down anymore because that's a prime number, but 6 can. And so 6 breaks down into 2, or 3 and 2 rather, okay? And so since I have these 2's here, okay, what I can do with the square root of 12 is that I can write it like 2 times 2 times 3, and then we're just writing out all of its roots, and then I have 2 times 2, which is 2 squared times 3, and then since my index of the root of my index, right, is 2, then the square root and this power of 2 cancel each other out. So what happens is that the 2 comes out of the radical, and what's left inside is the square root of 3. Okay. So now what I want to do is that I want to give you some more definitions to work with. So if I have some index for my radical here, and then underneath it it's u times v, I can break this apart into the square root of u times the square root of v, okay? And to see how that works, if I had, let's say the square root of 4 times 25, right? I would break this apart into the square root of 4 times the square root of 25. And I know what these are. So, because my index for my radical is 2, so the square root of 4 is 2, and then the square root of 25 is 5. And so 2 times 5 is 10, okay? But I could have even just simplified 4 times 25 underneath my radical, which is 100, and the square root of 100 is also 10, okay? So, just two different ways of looking at it. For some numbers, the definition may be easier to use when you're dealing with much larger numbers. And then the other definition that we want to look at is square root of u divided by v. And so we just distribute the radical to each of these. And so to see an example of that, if we were to have, let's see, I'll work with the cubic root this time, of 8 divided by 27. I would break this apart. And the cubic root of 8 is 2, and the cubic root of 27 is 3. So that would be my final answer right there. Unlike with the previous example, we can't simplify 8 over 27 because they don't have a common factor. So I actually have to go through and use the definition to evaluate this fraction. Okay, so moving on, if we wanted to look at some examples where we had variables instead, okay? So something like the cubic root of 64 times x to the 6, okay? How would I go about solving that? Well, I would have to use the definition where I break apart my two numbers here. So if I let this be u and then this be v, I get the cubic root of 64 times the cubic root of x to the 6, okay? And we know what the cubic root of 64 is. That's 4, right? But trying to evaluate x to the 6 and its cube root, I have to go back and look at my previous definition. So if we remember, if I have some number raised to the m power and then taking the square root with respect to n, then I have to use this definition. So I have 6 divided by 3, and 6 divided by 3 is 2, so my final answer is 4 times x squared. Okay? And if I wanted to look at some definition where or some example where I'm dividing, if I have the 5th root of, let's see, I think this will work. 32 divided by x to the 15th power times y to the 3rd. Okay, what would that look like? So again, I have to use my definition for division, and so I have the 5th root of 32 divided by the 5th root of x to the 5th times y to the 3rd. And now, in this denominator, right, I can split apart x to the 5th and y to the 3rd. So I still have in my numerator the 5th root of 32, and then I have in my denominator the 5th root of x. Oops, this is x to the 15th, yeah, that's right, x to the 15th. X to the 15th. Put that one there. X to the 15th times the 5th root of y. Well, let me fix that. Of y cubed. Okay. So the 5th root of 32. I want to think about that a little, and so, using my knowledge of radicals and exponents, since I am taking the 5th root of 32, I want to think of a number that when multiplied 5 times gives me 32. So I'll let you pause the video and give that a second to think about. Okay, so if you paused the video and thought about it, then you should have gotten that the 5th root of 32 is 2, okay? And so now we want to evaluate the 5th root of x to the 15th, and so that's x to the 15th divided by 5, and then this y cubed is y cubed divided by 5. And so 15 over 5 is 3, so I have 2 divided by x cubed, and then this fraction, it's as simplified as it gets. Okay, and so that would be my final answer for that. Let's see if there's any other type of crazy example to look at. Yeah, we could take a look at some negative radical. So if we want to evaluate negative, or the negative, let's see, 3rd root of 125 divided by 64 y to the 9th, okay? So using my definitions for division, I would have negative cube root of 125 divided by the cube root of 64 times y to the 9th. And then breaking apart my denominator, I would have the cube root of 64 times the cube root of y to the 9th, okay? And from here, it should be, you should be able to evaluate it. So the cube root of 125 is 5, and then the cube root of 64 is 4, and then the cube root of y to the 9th is y to the 3rd. And that would be my final answer, okay? So notice that the negative symbol, it never interfered with the radicals at all. It just stayed out front, and that's how you want to keep it. So just make sure that if you're trying to evaluate a negative radical, that you always keep that negative sign out front, okay? Alright, in the next video we will be looking at rationalization techniques. Just dealing with a little bit more complex algebra, and how we go about evaluating some more complex radicals. Alright, see you next time.